Assalamualaikum and good evening to my lecturer and my friend. So today we will conduct our lab 5. For the first one we do concentrate tube heat exchanger, and right now we set in counter flow. So as you can see, we need to maintain our water level, and we also need to maintain our temperature below 60. So right now we set our flow rate cold at 3 and heat also 3. Now we're going to set the cold side to 2. So let's see. Okay, let's see. 2. Right now we're going to decrease the cool flow rate to 1 liter per minute. What are you doing?
So right now I'm going to take the data.
Right now I'm going to decrease the flow rate into 0.5. What are you doing, Shafiq?
Okay, right now I'm going to take the data and complete it in the table.
Okay, nice. Right now, we are going to change from counter form to parallel form.
After we change to counter to parallel mode, so we need to start our experiment. So first we have to on the water pump. Then we need to switch on the main power. Second, we have to switch on the pump.
Okay, switch pump.
Second, we have to switch on the pump. And need to switch on the temperature controller. So now we have to wait for the temperature reach until 60 degrees Celsius.
When the temperature controller almost reach 60 degrees, we're going to increase the hot flow rate and cold flow rate to 3 liter per minute. I about to see.
Yes. Okay.
For the test one, for parallel flow, pH1 is 53.4, pH2 58.0, pH3 56.0, and pH4 is 32.4. For the cold flow rate, PC1 is 25.9, PC2 30.5, PC3 28.2, and the last one is PC4 30.6 Celsius. So right now I will explain how we come out the result from parallel table using raw data. For the test one, we set our hot flow 3 liter per minute, cold flow 3 liter per minute, and for the first temperature is 54.3, TH2 is 59.7, for cold 23.2, and TC2 is 28.3. From there, we can calculate the temperature efficiently, pH, PC, CPH, CPC until heat transfer coefficient. Same as counter flow, from the raw data we can calculate the other like temperature efficiently until heat transfer coefficient. As you can see, for the test one, we also set our hot flow 3 liter per minute, cold flow 3 liter per minute, and the first one temperature is 53.4 for hot, and TH2 is 57, TC1 25.9, and TC2 30.5, and we repeat the experiment until test 4.
Now we seeing is a graph that shows the temperature profile for parallel current flow, where hot and cold fluid enter the heat exchanger at the end and move in same direction. This is for test 1, test 2, test 3 and test 4. Now we seeing the temperature profile chart for counter current flow condition, where the hot and cold fluid enter the heat exchanger at opposite end and flow in opposite direction. This is for test 1, test 2, test 3 and test 4. For the second question, we need to create a chart of energy balance coefficient against the heater temperature. To create the chart, we need to find the energy balance of coefficient for both parallel flow and counter flow. The formula for energy balance of coefficient is CEB is equals to the rate of heat transfer of A over rate of heat transfer for E. This is the energy balance of coefficient for parallel flow and counter flow. This is the chart of balance of coefficient against heated temperature for parallel, and this is the chart of balance of coefficient against heated temperature for parallel.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firadaha and I'm going to explain the discussion number 3. For discussion number 3, we need to find the LMTD and use this to calculate the heat transfer coefficient, which is U, for each heater temperature. Then, we need to comment on how the heater temperature affect the heat exchanger performance. For the LMTD, we need to use the formula TH2 minus with TC2. Then we need to minus with TH1 minus TC1 over with ln TH2 minus TC2 over with TH1 minus TC1. Then we insert the data into the formula to find the LMTD for test 1 to test 4 for parallel flow and counter flow. After we find the LMTD for test 1 to test 4 for parallel flow and counter flow, we need to find the heat transfer coefficient, which is U. The formula of heat transfer coefficient is U equal to QE over A times with LMTD. Before we insert the data into formula, we need to find the A first, which is area. The formula of area is A equal to pi d power of 2 over 4. Then we get the answer A equal to 7.85 times with 10 power of minus 5. Then we insert the data into the formula to find the heat transfer coefficient for test 1 to test 4 for parallel flow and counter flow. The question on how the heater temperature affects the heat exchanger performance. The answer is the heater temperature can affect the heat exchanger performance because the greater the temperature difference, the greater the rate at which heat is transferred. That's all for me. Thank you.
Okay. For discussion number 4, compare heat transfer coefficient of the two heat exchangers. So, for the first test, the value of the counter flow, which is 4262.053, is more than the parallel value, which is 3632.102. As for the second test, the value of the counter flow is more than the value of the parallel flow. As for the test 3 and test 4, also show the exactly same situation, whereas the value of the counter flow is more than the value of the parallel flow.
My name is Muhammad Shafiq bin Sharif. My metric number is B0920103339. I would like to explain about conclusion. For the conclusion, the heat exchanger apparatus follows the basic laws of thermodynamics, and this can be shown experimentally. From all of the parallel flow configuration, the exit temperature of the hot fluid is always hotter than the exit temperature of the cold fluid. This supports the Clausius statement, in which heat may not spontaneously transfer from a colder body to a hotter body. From the other experiments that hold flow rates constant or vary the flow rates, it is clear that the first law of thermodynamics and conservation of energy apply to the heat exchanger apparatus. In practical application, the counterflow configuration is preferred for its higher effectiveness. Additionally, the counterflow configuration is also capable of have a cold fluid exit temperature that is higher than the hot fluid exit temperature. This was not shown experimentally. However, from the data collected, it is clear that the flow rates were too high to achieve this desired result. If the experiment were repeated with lower flow rates, it would be possible to demonstrate a situation where the exit temperature of the cold fluid is hotter than the exit temperature of the hot fluid. That's all from us. Thank you.